Well, let's start with the basics. How do you open up one of these things? First off, on most machines there is a power switch in the lower right hand part of the cabinet in the front. That will shut it off. I see people opening these with power on them all the time. You can. At least it's safer with electricity. You don't have, if there's a loose component in there, you're not having issues. A lot of times the coin door in the front will be locked. And then on almost all pinball machines there's a lever, and when you pull down on that lever the lockdown bar comes off, and that's pretty standard on most machines. I always close the lever and close the door again, and then you slide the glass out. Be careful where you put that glass. You don't want to put it on concrete or something like that because it can chip the glass. Once it's open, and that lever has to be down. This is the apron, and there's a handle right here, and you just lift up on it. And you can prop it open. You can prop it open like this. Most machines have a prop rod that let you put it up like that and work on it. Now, that's great, but you don't want to leave it like this for very long. I mean, like days, because the playfield can crack from the stress this is putting on it. Another way of handling this playfield is to prop it up what I think is called service mode. And I'll show you how to do that. So to put it up into that service mode, put your prop rod back down. Just lift the playfield up out of the machine and prop it up like that. You can really work in the back of the machine this way because when it's just propped up, it's hard to get up underneath there. So then you look at what you're dealing with here, and you might think, good Lord, what am I going to do here? There's all kinds of stuff here, and then let's look down inside the machine. All kinds of stuff in there and all kinds of wires. So the purpose of this video is going to be to kind of explain some of what's going on here. Let's look at the inside of this machine. The coin mechs are on the back of the coin door, and that's how back in the day you put quarters in there to get the machine to play. You add credits on. A lot of machines are set to free play right now, and even the coin mechs are removed. I heard that operators used to remove them so that the machines couldn't become competition again. Over here on this machine, this is a Williams Aztec. There's the knocker coil. We'll talk about it a little bit later. Here are the chime coils. The fuse panel is here. Then you've got various connections going to different pieces up to the front of the coin door, the tilt relay, and that kind of thing. Here's the transformer, incoming voltage. We'll cover that as well. Here is the Williams score motor. You can see lots of switches here. We'll talk about score motors later. And then back in the back, there are a series of relays. Again, stepper units. We'll talk about all that, but that's kind of the basic layout of most machines. They all look pretty much the same. Playfields will vary a little bit, but same components on them. So here's just a shot of the playfield. Here are some pop bumper coils. We'll talk about those in detail. Also light sockets, I'll explain how those work. I don't know, right here is a rollover switch. We'll look at those later as well. Standing target there. So these are probably the simplest coils on a machine. There are a couple like this. The knocker coil is just a coil with two leads to it. No switches, no nothing. When it receives voltage, the plunger, I can't get it to manually go, will hit this piece of metal, which makes the knock sound for a replay credit. Chimes are the same exact setup, just two wires to a coil, and those plungers hit the plates, and the plates are all different sizes, so they make different sounds. The most basic coil. So I haven't shopped this machine yet. It's not real pretty, but I wanted to show these are standing targets, and really all they are, there's a switch back behind that target. When the ball hits it, it closes and makes contact. And then over here you've got rollovers. When the ball rolls over these wires, it closes the switch on the underside of the machine. Pop bumpers. Here are a couple other switches. The pop bumpers, when the skirt is pushed down, that closes the switch in the underside of the playfield. I'll show that later, which triggers the pop bumper, which shoots the ball away. And then you've got a spinner. That rotating action is carried down below with the wire to a switch. Some of the older machines use these big clunky rollovers. They're like buttons. So I've got an old playfield. It's a salvage playfield from a machine, but it's got a good example of the simplest stepper unit on it. This is the Sky Jump. There's a multiplier control unit, and you can see a coil right here. It's just got 2 wires on it. There are no switches or anything. And then as that coil fires, watch the mechanics here. Now this thing is not lubed up and clean and functioning super smoothly, but it is functioning. And you can see there's a gear here. As the coil activates, this arm comes up, and this little lever here grabs a tooth and pushes it down. And through the use of these springs and the coil goes down, springs bring it back. It just keeps rotating this wheel. Now let's look on the other side of the stepper unit to see what's happening over there. Alright, so as I activate this stepper unit, you can see that disc rotating around. It only goes one direction, doesn't go back and forth. And then if you look, there are little shoes that make contact with rivets on this bakelite plate. And see, this wire here connects these 2 shoes together. So basically it's a switch that's moving across a set of rivets. That's one of the most basic stepper units there is. Here's a view of a flipper coil, and really pay attention to this end of stroke switch right here. As the coil activates, this little arm opens the switch, and that opening is what actually lets the second coil inside of this coil operate. Remember that a flipper coil has actually 2 coils in series into it, and the end of stroke switch shorts out one of them for the initial coil closing, which gives that flipper pop. And then once that end of switch opens, it puts the second coil in series in the circuit, which has higher resistance so that it doesn't burn up. Let's take a look at some light bulbs. Alright, so these are press fit together, and over time they are going to cause some issues. And I hope you can see there's a little black insulator right there. So light bulb is basically a really small coil, so it's going to need voltage across it. One part of the voltage comes in on the wire into this tip, and then it goes through. Let's see if I can show in the camera. Yeah, see that little silver piece in the middle? That's actually mechanically that tip. And then the outer barrel of this light bulb is the other side of the voltage. So the way the light bulb works is when electricity is applied here and on the outside, it's going to light the bulb. To handle that, the manufacturers press this barrel onto this metal and soldered on connections on the back. Incidentally, what can go wrong here is as those insulators dry up, you can get a bad connection between the barrel and the metal, and you'll get flickering lights or intermittent lights. The other thing that can happen is this mechanical connection between that tip and the spade where they put the wire on. That can have poor connection as well, and I've actually soldered the wire, moved it from here to the actual tip to avoid that mechanical connection. Here's a good example of a drop target. If you look here at these switches right here, I'm going to activate this. So this is obviously an upside down playfield. I'm going to activate this drop target, this white piece of plastic, and then as that happens, watch what happens here. There's a little silver arm. I'm going to do it in slow motion so you can watch it. See how that silver arm pushes out and closes those switches? That's how a drop target works. So that's how it would normally function. And then to reset, there's a big coil. Usually they're kind of heavy duty, and they just push all these arms back into place. Rollover switches are probably some of the easiest switches on the playfield. Those are those little pieces of wire I mentioned. Pretend a ball comes through there, and just watch this switch right here. Little piece of wire pushes that leaf up and closes the switch. Very simple. Here's another example of a light bulb too. There's that tip and there's 1 voltage, and then there's an insulator, and then the frame connects to the ground. So this is a pop bumper upside down. So remember that pop bumper ring is going to push down against the play field, which pushes those balls away. And what I wanted to show here is obviously there's a coil, 2 wires coming in, but there's a switch right here. Actually, there are 2 switches. Remember I mentioned that when the ball runs up on an apron, there's a little switch in here called the spoon switch that the apron moves around and closes the spoon switch. Hopefully you can see, just watch right here as it moves. It closes the switch. When that switch closes, it fires the pop bumper. Now, how do you keep that pop bumper from staying on all the time? Well, watch right there. There's a little switch right there that's normally closed, and when the pop bumper activates, it opens, which cuts voltage off so it doesn't fry. So here is an example of a stepper unit that counts up and then it resets all the way back down. So 1, 2, 3, reset. 1, 2, 3, reset. This is the coin unit on a Gottlieb. Some of the older Williams machines also did that for ball count. It would be ball 1, ball 2, ball 3, ball 4, ball 5, and then reset back down. Let's see what it looks like on the other side of that stepper unit to see what's happening. Okay, so I had it backwards. There's reset, and then here's 1, 2, 3, reset. So you can see there's a little rotating plate there. Same thing, shoes on rivets with little wires across. So here's the score motor. Score motors used to intimidate me quite a bit because there's so much on them, but they aren't that bad. Here's the tilt bob. If this thing's out of alignment and touching, it's going to always have a tilt. There are a couple other switches typically on machines, like a slam tilt on the coin door or on the bottom of the machine. I think even in the back box they can have them. Let's take a look at a relay. They're just held in place with a little clip here. It's like kind of like a cotter pin, but I don't know if that's the actual name for it. And then they just unclip from whatever bracket they're on. This is the Z1 relay on a Gottlieb Spirit of 76, and you can see there are all kinds of switches here and here's the coil. So when the coil pulls closed, it's going to pull this arm down, which is going to act all of these switches. If they are normally closed, they will open. If they're normally open, they'll close. And I think this one may be hard to see in the video, but you can see the switches opening and closing. Like watch that top one, it's closed, now it's open, closed, open. That's the basic functionality of a relay. Incidentally, you may, if you buy a machine and you want to move it, you have to take the head off. There are usually 4 bolts on the machine. You have to take out all 4 bolts, but before you do that, make sure you disconnect any of the wires going down into the bottom of the machine. And here's one. That's called a Jones connector. And they're real slick because on most machines you can't get them on wrong because they all have different number of little connections on them. But like in this example, there are 1, 2, 3, 4 Jones connections. Pop those off, put them down in the cabinet, take these 4 bolts off, and the head comes right off. I'm going to try a close-up of this step-up, step-down stepper unit. So this would be the third kind. Remember, the first one just went around in a circle. The second one would count up and then reset all the way back down. This one counts up and counts down. So there are 2 relays on it. And let's see here. Watch this little post right here as the stepper unit counts up. That's the bonus unit on this machine. And then there's a relay in the back which counts down, and it will go until that post opens a switch. And we won't get into the details of what that switch does, but just the main thing here is how the stepper unit takes a coil and makes a count up, count down, and makes a count up, count down function. Another relay type is a latch relay, latching relay. This is AX on a Gottlieb 4-player. And you can see 2 coils here, and I'm hoping the camera catches this. So what happens is one coil will go And mechanically, did you see that little plastic latch? Well, it pulled these switches down and then latched on, and then to unlatch, this coil goes and it snaps back up into place thanks to this spring here. So it's either latching on or off. And it's a way for the coils not to have to stay on all the time. So let's get started with some basics. So let's talk about electricity first. Number one, electricity can kill you. So be very careful when you're working on pinball machines because it's a fun hobby, but if you don't know what you're doing, you can get shocked, you can get severely hurt. So if you don't know what you're doing, stop. Get somebody who does know about electricity to help you. This is only a brief overview to kind of show some of the things you can do. And one of the ways that you can avoid hurting yourself on a pinball machine is to work on it with the power off. And you can use an ohm meter. And maybe in a later video I'll cover some of the things you can do to troubleshoot with no power on. But for right now, if we just think about electricity, typically there is some kind of resistance. That's a horrible symbol. I apologize. And then an electrical circuit comes like this. There's either a battery or a generator here. And it creates a voltage. And then as that voltage, as the current flows through the resistance, that's an electrical circuit. And then, so what's going to happen, depending on what that resistance, what's making up that resistance, it could be a light bulb that would turn on. It could be a coil, which energizes. So hopefully the theory about electromagnetism is something that you've all seen, where you could, for instance, take a nail and wrap a piece of wire around it and then hook it to a battery, and the nail becomes an electromagnet. Well, a coil is very similar on a pinball machine. It's just a big coil of wire with a hole in the middle. It looks like something like this. And all that is a bunch of very small wire spun around, and then it's going to have two leads hanging off. And if you hook electricity to these two leads, like if this right here was a coil, when you apply electricity to that coil of wire, it creates a magnetic field. And in every coil on a pinball machine, there is a plunger. And that plunger, when electricity is applied to the coil, it's going to push that plunger in the opposite direction. And then typically gravity, when we release voltage, gravity will let that drop back down. That's what you see on a knocker. It would actually be turned this way, and the coil would fire and then just drop back down. Anyway, so one thing about the electromechanical pinball machines is they use AC voltage, alternating current voltage. So we don't have to worry about direct current positives and negatives. And we also don't have to worry about a voltage scaling from 0 to some number. The way the machines were built, it's either on or off. The voltage is either applied or it's not. There's not like 0, 2, 4, 6 volts. It's either 0 or whatever the voltage is on the machine. That's very useful in troubleshooting, because really all you're looking for is, do you have a circuit path? For instance, in this case, we could add a couple switches. Let's just, we're going to add a switch here and a switch here. And then let's say our power source is here, and the symbol probably isn't right, but we'll call it a generator. I think that's a galvanometer symbol, but we'll call it a generator. Well, as long as there is an open switch, the current cannot flow. And we could close one switch, and this will be a symbol we'll see later. It's a normally closed switch. This is a normally open switch. We're still not going to get contact. So let's draw this slightly differently. Let's say that this line and this line represent the generator. And then right now we've got this coil, and we're not going to use this very bad resistor symbol. We're going to use the coil symbol from the machine. And then on either side there's a switch, right? So if we're saying there's always voltage here, and let's just say there's 25 volts AC there, we can't get this circuit to close until both switches are closed. Well, one is closed right here, but we still don't have a path. We still don't have a way to get from one voltage to the other, one side of the voltage to the other, until we close this switch. At that point, we have a circuit. We have both ends of this generator connected to a coil, which is going to allow current to flow, and that coil is going to do something. That's the basics of the operation of coils on machines, on pinball machines. Same thing applies to a light bulb. If we have a light bulb symbol and we have a switch, and we only have one switch, let's say, that light bulb's not going to turn on, because if we have a generator, you know, it's connecting from this end of the switch all the way around, the generator's running, but we don't have a circuit. As soon as we close that light bulb will light. Those are the two basic operations on a pinball machine that you need to keep in mind. So let's look at what a layout of a pinball schematic is going to be. If we say, we'll start at the bottom. Typically at the bottom you're going to see something that looks like this. And these go, usually these come down to an electrical plug. They'll show it somehow, depending on the schematic. But this is the transformer. And what happens on the transformer, it brings in the 110 volts AC from the plug, and then it steps it down into two separate voltages. And on the machine that I'm going to use as a reference, which is the Gottlieb Spirit of 76, which I believe most machines use these, but you'll have to check your schematic. It's going to provide 6 volts and 25 volts. 6 volts is for the light bulbs. 25 is for all the coils. And I did leave out one thing that is kind of critical. I'll just draw one in here. You'll see a symbol that looks like this. And that's a fuse. And they should say like 15 amp. And this would actually be done in here, but just for example. But that's a fuse. And then a lot of times what you'll see is a color listed here. You might see something that says red. And I'm just making that up. And this might be red-orange. That is a good way for you to be able to identify where the fuse is that you're looking for. Most of them are labeled. They tell you what amperage, but those labels can fall off. You got to be really careful here, because you don't want to put too high a fuse in there. Never put in a higher rated fuse than what's specified, because that will cause serious cooking of coils and stuff. If you have a short somewhere and you put in a bigger fuse to avoid blowing the fuse, you're going to cook something later on. So let's take this up, because usually a schematic is a very long diagram, or a long sheet of paper. It's like 3 feet long, 2 feet long, and it's divided into 2 halves. And usually this 25 volts, you're going to see something like this, and then the 6 volt is going to go up like this, and then over like this. And then what you'll see usually here is all kinds of information. You'll see a legend. You'll see a coil list. You'll see a motor sequence chart. You'll see, what else? Color codes for wires. So that lower left a lot of times is where a lot of the information about how to read the schematic is. You might see a score motor diagram, which are very useful. And then up above that is going to be all the lighting, at least on this reference schematic, and I've seen this is kind of similar everywhere. And then on the right is the 25 volt side, the coil side. So now let's come up with an example to show that. So we'll draw our, we'll work on the 25 volt side. We'll put in a couple lines. And again, this represents the difference of voltage potential on that generator. If you were to connect a wire across there, if you were to hook a resistor across there, it would put 25 volts across that resistor and generate the appropriate current depending on the resistance of that resistor. Now we're using coils here, and let's draw in a little circuit here. Let's say that we want to, and I'll try to come up with something here that also represents logic, some logic that could be used. We'll have a coil, we'll call it A, coil A, and we'd have some clever name for it later. And we'll have a switch here, and we'll have a switch here. So if those two switches close, the A coil is going to fire. Now I'm going to connect in another switch here, and I'll explain why in a minute, and we'll make this normally closed. So, and we'll just call this, well, I won't label those just yet. And then we've got another one called B. And let's see, it'll have two switches as well. One's normally closed. All right, so as you can see right now, there is no clean path for either one of these relays, or either one of these coils. These coils cannot energize without a complete path between the two sides. This is a symbol for a coil, this is a symbol for a switch contact or a switch. So the naming convention on these old schematics, the A relay, any contact that is on a relay just has the same letter on it. And what I would prefer if they would have named them something like coil A with a 4 behind it, to let you know there are 4 contacts on that relay. When that coil on the relay closes, 4 different spots are going to have switches close. And then you could name the switches 4.1, 4.2, 4.3, 4.4. Unfortunately, I can't go back in time to change the way they did it. So we're stuck with what we've got. So we're gonna make this a rollover switch on the pinball machine. And then we're gonna do something they do fairly commonly. We're gonna call an A switch. And this is a fairly common setup on pinball machines. Let's say that a ball runs over this rollover and closes it momentarily. Well, now you've got a circuit all the way across that voltage, which means that coil is going to energize. Since the coil in this case is a relay, it's going to pull down that arm of switch contacts. One of those switch contacts is right here. See the A? It's going to close because the relay is pulled down. Even though the ball is not on this rollover anymore, this opens up. What you've effectively done is made a permanent connection across here so that A relay is going to stay on until it's interrupted. That is how a machine handles a momentary switch closure, making it into something longer. Now let's say that another switch contact is down here. And this is how machines can make a ball running across a spot in the field have multiple actions. So when A enables, it's going to close this contact here, which means now the B relay or B coil is also turned on. And let's just say, for the sake of argument here, let's put in a light, and we'll just have one switch, and that is B. So in this case, B will close, and you know what? Let's do same thing here with a B contact. So it will keep the B relay energized all the time. So then this will close and that light's going to stay on all the time. So let's recap it real quick to make sure everybody's tracking. The ball rolls over a switch. We have a circuit to the A coil. A coil energizes, so A coil is going to close, A contact is going to close here to keep the A coil on. And then the A coil is going to close here. And now we'll have a circuit to the B coil. B coil is a relay, it energizes. It closes a hold-on switch here so that the B coil stays on all the time. And another switch on the B coil lights a light. And that's basic pinball operation. Let's cover these normally closed switches here too. In the scenario we provided, rollover enabled A, which enabled B, which enabled the light. So the light's on the playfield. Somehow you're going to have to shut that off, whether if it's a pinball machine with multiple players, or maybe the ball drains and the ball return relay is here, maybe ball return, and that would be like it could be relay C, and when the ball goes in the out hole, it might open that switch, which disables B. And also keep in mind that typically A is going to do more than these two things. Yeah, it's gonna have a hold on relay, and then it's going to enable B, but the relay could have anywhere from 2 to 8 sets of contacts on it that could do other things. So even though A turns on B, it probably turns on some other things as well. It could fire the score reel. You could get, when you hit A, that rollover, you probably are going to get some points. You're going to turn on this light. You're going to do some other things. So that's why these normally closed switches are key, because they really help drive the functionality of a machine. So where it can get really interesting with these pinball designs is when the designers combine a score motor with a varying set of logic. And I'll try to show an example here. Let's say we've got a switch here like this, and then it comes over and it has 3 paths. And then let's say, we'll just make this up as we go. Let's say this is a 100-point relay. And then this one is a 1,000-point relay. And then let's say this is an add bonus relay. Now, you can look at some of the episodes from the Pinball Torture Test series I did on how a machine works, and it has actually some examples similar to this. And we'll just say that there's a motor switch that pulses 5 times. And when the motor turns and 1C closes, depending on which one of these switches are closed decides what happens. So there could be something on the playfield that closed this 1,000-point relay, or 1,000-point contact. When the motor runs again, it's going to get 5,000 points. Or it could toggle between 100 and 1,000. So one of these is closed at any given time, and maybe it's a rollover switch on the machine, triggers a relay that either toggles back and forth between 100 and 1,000. It could be a case where you hit a target on the playfield that adds bonus, or another rollover. This is where the designers really got clever, because by using that same switch that motor 1C5 pulses, you can do all kinds of different things. That's where it kind of becomes a spider web on the machine, as you might have one relay that causes 4 other relays to do something, and then those 4 relays might trigger 2 other relays each. So one action can really drive a lot of activity on a machine. And startup, I think, is a key example of that. A Gottlieb 4-player startup is not trivial, and I'm hoping to explore that in a future video. But it's easier, I think, to fix problems if you have a known issue on your machine and you can work your way back from that particular relay. For instance, let's say 100 points doesn't work. Well, you can look at the 100-point relay, and on that relay there's probably going to be contacts for a chime, the score reel to add 100 points, and maybe some other things, maybe light something. If none of that's working, you can look at the 100-point relay and see if you've got a problem here with a connection. It's a lot harder, I think, to look at startup sequences than it is to fix individual problems, but the goal here is to understand it well enough to even be able to troubleshoot startup, which is where some of the more complex problems can come up. Now let's look at some other symbols you may see on a schematic. So one thing you might see, let's see here, we might be able to do a few things. You'll see a score motor. Might look like something like this. And then depending on the machine, it may have a bunch of switches like this. And these might be A, B, C, D, E. That notice how these are all in parallel now. They're not sequential like this. And there's a big difference here. Because for that coil, this is a B coil, for that coil to energize, all 4 of these switches have to be closed to make that circuit. On this score motor, since they're in parallel, only one of these has to close, and then you've got a circuit. That's the difference between series and parallel, and it's something you really have to watch. And I think the point here is always look for that circuit path. And any one path is all you need. Like in this case, you don't need 5 switches to close, you only need 1. But in this case, you need all 4 to close. Something else that you might see might be, as I mentioned before, you might see a normally closed switch. You might see something that looks like this. And ignore the logic here, but this might be a little arrow like this, and it might be C. And what that's saying is that when the C relay energizes, the contacts toggle. You might see that. You might see something that looks like this, a little arrow, and then 2 circles. And don't worry about these, but this might be like 3 ball and 5 ball. So depending on how you set the machine, this is how it symbolizes the difference. You might see something that looks like this. And a series of connections, and then like a bar here. And then each of these goes somewhere. And then you'll probably see a dotted symbol around it. And it might say, it might say thousands unit. And in this case, this might be how we get a credit if we hit a certain score. If you look on a Gottlieb Spirit of 76 machine, this is a continually moving contact on the score wheel that might hit 0, 1, 2, 3, 4, up to 9. And that's how you get like 6,000 points on 76,000 for a score free game. I think lights are pretty simple. It's the same symbol. You might see something where, like, if a switch closes, multiple lights turn on. Maybe something like that. Or you might see lines with an individual light for each contact. I think finally you might see on the flippers, you might see something that looks like this. Boy, that's a horrible line. Boy, that's really bad, sorry. But what this is showing, this might be an example of the flipper, where, remember I mentioned that there are 2 coils inside the flipper coil, and there are 3 leads on a flipper coil, and this is the end of stroke switch. So when a flipper is first pushed, this is closed. There's going to be a circuit here to this smaller coil. Smaller coil has smaller resistance, so it's going to have more current, so the flipper is going to pop harder. And then once that end of stroke opens, the entire coil comes into play, which prevents the player from burning up the coil by holding the flipper button too long. Here's something else you might see. This is on the coin unit on the reference schematic. You might see something like that, and then wires like this. And then what that's saying is, as the coin unit is operated, it's going to move down and connect different circuits. So it's a way to show what happens as the coin unit stepper is incremented. And I think one key point here is we'll always watch for these dotted lines because those typically refer to a unit, and that's typically going to be a stepper unit. And you might see different sections for the same unit. They may show up in different parts of the schematic. But usually a dotted line like that means look at the stepper unit or score reel or coin unit or bonus unit. They really help you understand where those units are and how they operate. And one last warning about these units. For instance, a bonus unit might have a bonus position 0 switch nowhere anywhere near this unit. It's going to be completely in a separate part of the schematic. Those are tricky, so you really have to watch line by line on a schematic and understand the switches that are in the circuit. For instance, back to this guy here. This might be bonus position 0, and it would say that. And then this might say C, which means the C relay. So if B is not working, you have to look at all 4 of these to figure out which one is not working. And I think maybe in a later video I might show how to troubleshoot that with an ohm meter. Depends. If I get feedback that this is useful, I might look into it.